We are going to use our t-test simulation spreadsheet to show the calculation of t-tests. And just to remind you, we are doing the same study 1,000 times. You, of course, only will do it once, but in our simulation, we are pretending as though we are doing it 1,000 times. And we're going to compare two groups, Group 1 and Group 2. And in this first example, we are going to test the null hypothesis. In other words, the true, or we're doing a t-test in which case the null hypothesis is in fact true. Both groups have a mean of 100 and a standard deviation of 16. So this is the situation of the null hypothesis. Now, if we look at 99.6 as the first sample, 94, you can see that even though the means we're sampling from distributions with equal means, the actual sample means are different. We talked about how they overlap with the true mean if we look at the confidence intervals. And then here is the t-test. I froze my panes right here so that you can see Group 1, Group 2, and the effects of the Group 1 versus 2 t-test. The difference between the means is that, and so that in this case is minus 5.5. So we take K8, Group 2, and we subtract from that A8, and we get a negative number. So if we were to just do this study, we'd think, oh, well, they're different, they're minus 5. But when we do a t-test, we're going to first calculate the standard error of the difference. Now, what is that? You can see on your agenda sheet that I printed out the formula, but this is what it looks like in Excel. We take the square root of D8, which is the standard error squared, plus N8, the standard error of Group 2 squared. Take the square root of that to get the standard error of the difference. Now, there's a very important feature here, and that is that the standard errors are squared and they are summed. We don't take the average. It is not the average standard error. This is very important. It is the sum, which makes it a lot bigger. Variability is a lot greater than just the individual ones by themselves. So then, once we have the difference in the standard error, a t-test is an estimate of a parameter divided by its standard error. You can do this with kurtosis, skewness. We're doing it here with the difference between means. You can do correlations. You can do regression coefficients. Well, not correlations, but you can do regression coefficients. You can do all sorts of things to find if they are significantly different. And so in this case, the t here is the difference AE divided by the standard error of the differences. And so the value is minus 0.8. And you think about this, so the standard error is an estimate of the standard deviation of the sampling distribution of differences. We can see here that if we go ahead and calculate the p-value, which is done with this t-dist function, and the t-dist function only likes positive t-values, so we have to take the absolute value of this t, and the degrees of freedom are n1 plus n2 minus 2, that's 18, and then this is a two-tailed test. So the p-value is 0.463. Now here I have, so we've done this 1,000 times, and then I have looked to see how many times does this p-value exceed 0.05. In other words, how often is it not significant? And in this first case, the p-value is 0.463. And so we ask, is that number greater than 0.05? And if yes, then we give it a 1. If no, we give it a 0. And when we sum all of these overlaps, we notice that the number is 966, which we're doing a two-tailed t-test, and we're using a probability of 0.05 as our criteria. So that means if the null hypothesis is true, 95% of the time we should not reject the null hypothesis. And so that's what we find, that it's pretty close to that. It's 966 times, which is close to 950. So we were wrong. So there's values in here where in fact we didn't reject. In fact, here is one right here. And notice our P was 0.019. So the difference was 14.9. In this case, 99 versus 94 is, oops, that's not right. It's this one. 91 versus 105. And that difference was 14.9 with a P of 0.019, which is less than 0.05. So even though we're sampling from distributions with 100, where the null hypothesis is actually true, we are making a mistake here. We are rejecting the null hypothesis. This is our type 1 error. This is a type 1 error. It has rejected the null hypothesis when the null hypothesis is true. And in this situation, if 1,000 people did this study, 50 poor souls would have rejected, or in this case 34, but in the long run, 50 people will reject the null hypothesis when the null hypothesis is actually true. 1 out of every 20 people will come to the wrong conclusion when the null hypothesis is exactly true.